In this video, we will have to deliver. We will have to take all the particles and from them to produce a single, most plausible solution. If you remember, we had n particles, which means n different guesses. So 1000 particles means 1000 guesses. This is great, but we need to take all those 1000 guesses and just pick the best guess, the best solution for our system. How do we do that? I will give you a few methods to do it, and I will discuss the pros and cons of each one of them. Let's start with the simplest of all. Pick the best particle. Just sort all the particles by their weight and just choose the particle with the highest weight. If you have enough particles, this method will produce a very accurate solution. A slightly more advanced method is to take into account all particles. And by taking into account, I mean an average of all the particles. For example, let's say that I'm interested in a 2D localization problem and I need to find the XY value of my robot. How do I do this? I take into account all the X values and average them. It goes like this. The mean X will be sum of all Xi divided by N. N, which is the number of particles, and Xi, which means the X value of the ith particle. Now, a slightly more advanced variation of the average is the weighted average. And in the weighted average, we are taking into account not only the particle's data, but also its likelihood, its weight. So this equation becomes the following. So the mean X value will be sum of Xi Wi divided by sum of Wi. Now the last, most advanced option is to taking the average around the best particle. What do I mean? So let's say that I have many particles and this one over here is the best particle, the particle with the highest weight. So what do? We take a cluster of particles in the vicinity of this best particle. It looks like this. And from that cluster, we take the average of all particles. This is like an advanced weighted average. And this method will give you the most accurate and robust results. Now, there is an inherent difference between the first method and the other three. And the difference goes like this. When you pick the best particle, you pick only plausible solutions. In other words, you pick places or positions or states that your robot might actually be at. But when you take the average or the weighted average, you can sometimes end up in a non-plausible place, in a place that is not restricted to the problem's constraints. Let me give you an example. Let's say again that this is the best particle. And here we have a wall. This is a constraint. No particle can be inside the wall. Now, when I take the weighted average of all particles, I might end up with a particle being inside the wall. Now, this is impossible. I cannot be inside the wall. So it's very important when you choose the average or the weighted average, after you compute your best estimate, you must go back and see whether this estimate is plausible, lies within the constraints of the problem. This is very important to mention. This is very important to remember. I know what you're thinking. You want to see real-world problem, real-world examples when I can fit this theory into. So wait, you just got it. This experiment is part of a very big research we have conducted in a real university. So we started the experiment over here and we walked to the right and then down and then left and then up. A pedestrian route in a rectangular shape. Now, in order to do the localization, we utilized the particle filter algorithm. And in order to pick the best particle, in order to pick the best estimate, we averaged across all particles. So one can see very interesting results. What happened is that in the beginning, when the particles are still roughly spread within the region of interest, the particle produces poor results. This is inaccurate best estimate. But after several iterations and after several resampling process, the particles start to converge. And when they converge, the average estimate becomes more and more accurate. And you can see this very phenomenon in this graph. As you keep going, the particle's best average estimate becomes more and more and more accurate. And this is an important lesson. And the lesson is that reporting the true position in a particle filter only after several iterations. There is almost no meaning to reporting the best solution at the beginning. You need to let the particle filter resample and re-resample and let the particles converge.